Let's talk about linear first-order differential equations. First, what do we mean by a linear first-order differential equation? The order of a differential equation is the order of the highest derivative. So in this case, let's say we have a differential equation of this form. The highest derivative would be an nth derivative. You've got a y, you've got a y prime, you've got a y double prime, all the way to the nth derivative. This would be an nth order differential equation. A linear differential equation is of this form. So you've got a0 of ty plus some function of t times y prime plus some function of t times y double prime, etc., equals f of t. That's a linear differential equation. So you're not going to have a y prime squared in it. You're not going to have a y prime times y double prime. You're just not going to have stuff like that. That's not permissible. So for example, find the order of the differential equation and state whether it's linear or nonlinear. This is a first-order differential equation because the highest derivative is a first derivative, and it's also linear. Let's move the y to the other side. Now, notice that it's a function of t times y prime, dy dt, plus some function of t, in this case that function of t is negative 1, times y, equals some function of t. First-order linear differential equation. This next problem is complicated, but it's a cool application of first-order linear differential equations. Consider a pond which holds 1 million liters of water. So we've got the pond here. Got the fish in the pond. Let's draw the fish this way. The pond has one stream flowing into it at the rate of 600 liters per minute, and one stream flowing out at the same rate. Suppose at time t equals 0, a factory begins to pump salty water into the stream. Okay, in other words, into that first stream. Here's our factory. It's got this gross outflow of salty water. Blah, 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 blah. Pump salty water into the stream so that the salt concentration of this stream is 0.1 grams per liter. Assuming that the outflow is perfectly mixed pond water, determine when the concentration of salt in the pond will be 0.05 grams per liter. Okay, here's how we solve such problems. Y of t is the amount of salt in grams in the pond after t minutes. dy dt is the rate of change in that amount of salt. That's how we define a derivative. It's the rate of change. So dy dt is the rate of changing the amount of salt in the pond in grams per minute. And we're going to find a differential equation for dy dt by calculating the input rate and subtracting the output rate. Okay, let's find the input rate. The input rate is going to be the volume times the concentration. The volume, the rate at which water is flowing to the pond, is 600 liters per minute. We were told that. The concentration of salt in the pond, or in the stream I should say, is 0.1 grams per liter. Multiply that together, and we're given the rate at which salt is flowing into the pond. That's the input rate. That turns out to be 60 grams per minute. The output rate's a little trickier. Okay, so it's still volume times concentration. The volume of water flowing out of the pond is, again, 600 liters per minute. And here's the concentration of salt in the pond. At any given time, the amount of salt in the pond is y grams. That's how we defined it. Remember? Y is the amount of salt in the pond. So y is the amount of salt in the pond, or the mass of the salt in the pond. When we divide that by the volume of the pond, we get the concentration. So it's y grams per million liters. Multiply those together, and you get an output rate of 6y over 10,000 grams per minute. So this is the input rate. This is the output rate. Subtract them, and you're going to get this, okay? The input rate, 60, minus the output rate, 6y over 10,000. This may not look like it, but it's a first-order linear differential equation. We call it a first-order linear ordinary differential equation as if this form, so we're almost of that form. We basically just need to move that to the other side. Okay, here's how we solve a first-order linear differential equation. We divide both sides by a1 of t, so we just have y prime. We don't have a1 of t, y prime. So we want to have dy dt equals some function of t times y equals g of t. And again, we're just dividing both sides. We're dividing everything by a1 of t, so we just have y prime. We end up with something that looks like this, and then we multiply both sides by this complicated expression. We're going to call that an integrating factor. We do that, and we get e to the integral a of t. Again, that's where a of t comes from. E to the integral a of t, dy dt, plus e to the integral a of ty, equals e to the integral of a of t, g of t. So why on earth would we multiply both sides of the equation by this thing, this integrating factor, e to the integral a of t? It's because the left side is the derivative of y e to the at. So you can do the math if you want to, but that left side is just the derivative, y e to the at. Okay, so we've got this hairy expression like this, and enables us to integrate both. Oh, it's okay. So the e to the integral a of t enables us to integrate both sides. We integrate both sides with respect to t, and we get the integral of this left side here, kind of hairy, equals the integral of the right side. And again, this stuff here, all of that, that's just y e to the integral a of t, because I told you a moment ago that this hairy expression is the derivative of y e to the integral a of t dt. So then when we integrate it, we just get y e to the integral a of t dt. Okay, on the right side, you just hope you can integrate that. You probably can, because these textbook problems tend to be artificial. So let's solve the above example. We had dy dt equals 60 minus 6y over 10,000. We want to get it in this format. So to get it in this format, we need to move the 6y over 10,000 to the other side. So we have dy dt plus 6 over 10,000y equals 60. Okay, so now we've got it as a first order linear differential equation. That would be our a of t. That's the function that's in front of the y. So we have dy dt plus a of ty equals g of t. That's our function g of t. Okay, so in this case, that function a of t is 6 over 10,000. So we multiply both sides by the integrating factor, e to the integral a of t. So we have e to the integral 6 over 10,000 dt, because a of t is 6 over 10,000. The antiderivative of 6 over 10,000 is 6 over 10,000 t. In other words, 6t over 10,000. Okay, so we multiply both sides by the integrating factor, e to the integral 6t over 10,000 on both the left and the right sides. We integrate both sides to get this. Again, the left side looks so complicated, but it just always works out to be y times the integrating factor. So just don't sweat, okay? Just hang on. It's fine. So we have y times the integrating factor. It's always going to work out that way when we integrate the left side. Equals the integral of the right side, namely 60 e to the 6t over 10,000 dt. We know how to integrate that. Okay, you got the 60, the antiderivative of e to the 6t over 10,000. That's going to be e to the 6t over 10,000 divided by 6 over 10,000. You remember that from calculus too, from way back when. So we have this plus c. Dividing by 6 over 10,000 is the same thing as multiplying by 10,000 over 6. We do a little bit of cancellation. The 60 and the 6 cancel somewhat. And we're left with 100,000 e to the 6t over 10,000 plus c. That's our solution. Okay? So again, this is the left side. That's the right side. We're going to get y all by itself. So we're going to divide both sides by this. E to the 6t over 10,000. We end up with y equals 100,000, because this cancels with the e to the 6t over 10,000 you divided both sides by, plus c over e to the 6t over 10,000. Now we can find c in this problem. If we weren't told an initial value, that would be our solution. That's the general solution to the differential equation we saw just a moment ago. Okay, the general solution to this. But it turns out that we can find c because this is an initial value problem. Y of 0 equals 0. At time t equals 0, that's when the factory begins to dump the salt into the stream. So at time t equals 0, there's no salt in the pond. That just starts at 0. So we plug in t equals 0. Okay, so this is what our equation looks like. Plug in t equals 0, plug in 0 for t. 0 for t here. We know that y of t, we know y of 0 is going to be 0. And we want to know when the concentration will be 0.05 grams per liter. Okay, so let's see, all of this stuff. So again, y of c, blah, 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 blah. So again, we want to know when the concentration is going to be 0.05 grams per liter. The concentration is the amount of salt divided by the volume of water. So in other words, it's going to be this amount of salt, y of t, over 1 million. Well, we actually know what y of t is. Y of t is going to be this expression. We just saw that a moment ago. Okay. So let's plug in some numbers. So when you divide by million, the right side is just 0.1 minus 0.1 e to the negative 60 over 10,000 equals 0.05. Okay, that's going to be our concentration. So this expression, this whole expression, is going to be equal to 0.05. Let's subtract 0.1 from both sides. We end up with this. Negative 0.1 e to the negative 60 over 10,000 equals negative 0.05. So this is what we've got. Next step, let's multiply both sides by negative 1. Don't want those negative signs. And we end up with this. Let's divide both sides by 0.1. We have e to the negative 60 over 10,000 equals 0.5. We'll take the natural log of both sides. We get negative 60 over 10,000 equals natural log 0.5. So now we just multiply both sides by negative 10,000 over 6. We get t equals negative 10,000 over 6, natural log of 0.5, or 1155.2. 1155 minutes, that's 19 hours and 15 minutes. So that's how long it's going to take for the stream to reach that desired, or for the pond to reach that desired level of salt concentration. 19 hours and 15 minutes. Okay, here's a simpler one. Here's a simple linear first order differential equation. Solve this one. dy dt plus 2 over ty equals t minus 1. This is also a first order linear differential equation. The integrating factor is going to be e to the integral a of t. This is our a of t here. So e to the integral a of t is e to the, pardon me, coughing a little bit, e to the integral 2 over t dt. Oh, we know what the antiderivative 2 over t is. That's 2 natural log t. I'm going to write it like this, e to the natural log of t squared. Remember one of those log rules? You can put the t, you can put the 2 up there. Oh my goodness, we've seen this before. E to the x and natural log x are inverses of each other. So e to the natural log t squared is just plain t squared. That is our integrating factor. We're going to multiply both sides by this integrating factor and integrate. So again, here's our differential equation. Multiply both sides by t squared. We end up with something like this. T squared times this hairy expression equals t squared times t minus 1, which you can expand out like that. And then we integrate both sides. Integrate this. Integrate this. We know what the left side is. It's always going to be y times the integrating factor, yt squared. The antiderivative t cubed minus t squared is t to the 4th over 4 minus t cubed over 3. Divide both sides by t squared, and we end up with y equals t squared over 4 minus t over 3 plus c over t squared. And again, that's because we're dividing both sides by t squared. So now let's solve this differential equation of y of 1 equals a half. This is an initial value problem. So again, same problem. Now let's say y equals a half. This would be the general solution to the differential equation. If we know that y of 1 equals a half, we're just going to plug in t equals 1 and y equals a half here. And when we do that, we end up with a half equals 1/4 minus a third. In other words, a 12th plus c. Oh, I'm sorry. That's going to be negative a 12th. So that's negative a 12th plus c. So we have 1/2 equals negative 1/12 plus c. Let's subtract half from both. So we're going to add a 12th to both sides. So you have 1/2 plus a 12th. Sorry, I forgot that minus sign earlier. And c is going to equal 7/12. Sorry about that, folks. Okay, so that's our differential equation. We know that c equals 7/12. So we end up with y equals t squared over 4 minus t over 3 plus 7/12 over t squared. If you put the 12 on the bottom, you end up with this. Y equals t squared over 4 minus t over 3 plus 7 over 12t squared.